All right, hi everybody.
Hello.
Today we're going to do section 7-8. Section 7-8 is on improper integrals. This is another, what I would consider a BC only topic, but is a standard. You'll do this as a Calc 2 student sort of situation, okay? So what I want to do is I want to start by talking about why we call this an improper integral. So let's take, for example, the integral from 1 to infinity of 1 over x squared dx. How much area is that area under the curve?
That's infinite.
It's unbounded, right? Well, here's the thing. Maybe infinite area, maybe not. But here's what I would say is the area under the curve is unbounded. That much we can say, right? That's not closed. It's going on forever in some direction. Okay? So you can have a improper integral because one of the bounds is infinite. Or take an example of the integral from 0 to 1 of 1 over x squared. Again, this area under the curve is unbounded because it's occurring at a vertical asymptote, right? One of the boundaries is a vertical asymptote. So again, that area under the curve is unbounded. Does that feel okay? So those are the two types of improper integrals you can get. One that butts up against a vertical asymptote or has like a vertical asymptote occur in the middle of the interval you're integrating over, or your integral is to positive or negative infinity. Everybody's okay with that idea? Could both happen? Definitely, right? I could easily done 0 to infinity and then had both going on. I have an asymptote unbounded at one end and unbounded at the other, right? Could I have multiple asymptotes happen?
Yeah.
Yes, right? So like you might have to do the technique we're going to talk about multiple times in the same integral. And that's okay. It's not too big of a deal. So the idea here is, what we're going to do is we just make a substitution for the problematic bound. So in the case of we're integrating from a to infinity, we replace the infinity with a t and just stick the limit as t goes to infinity in front. Now we don't have to try to plug an infinity into our antiderivative. We can just evaluate this thing with a limit and it's going to be okay. I can do the same thing if the lower bound is infinite, right? Same idea. What if both the upper and lower bounds are infinite? Then I'll just split the integral at some value, arbitrary value a, and then I can do the same trick to each of these integrals by replacing the infinite bound with a t and then take the limit as t goes to infinity or negative infinity respectively. Is everybody okay with this plan? Yeah. If it has an asymptote, so we're say that f is continuous on the closed interval from a to b, but discontinuous at b, i.e. there's a vertical asymptote there at b. We'll do the same thing. We'll replace the problematic bound with a t, and then just take the limit as t goes to, in this case, value b from the left. And I know it's from the left because b is like the end of my interval, right? If b was the start, it would be b plus. Everybody's okay? And it doesn't matter if it's the, like which end of it is the asymptote's at. If it's at the lower bound, we do the same thing, but we use a plus. What happens if the thing is in the middle? Like the asymptote's in the middle, then we break at the asymptote and we have, like a t at the bottom and a t at the top, and we do plus a and minus a. Everybody's okay? All right. You ready to do some examples? This is the technique. This is the whole idea. Okay? So it's just basically replacing the problematic bound with a limit. Now, piece of vocabulary here. We say one of these improper integrals is convergent if its answer is a finite value. We say it's divergent if it evaluates to an infinite. So positive or negative infinity, which we imagine can happen if the areas are unbounded, right? That could happen, but it doesn't have to. All right, so let's look at the integral from 1 to infinity of 1 over x. First things first, 1 over x could have a vertical asymptote. Where's the vertical asymptote at for 1 over x? 0. Is that included in the bounds of integration? No, because we're going from 1 to positive infinity, so that part doesn't matter to us. The issue is the bound to infinity, right? So we're going to just take the limit as t goes to infinity of the integral from 1 to t of 1 over x dx. Everybody's good? Okay. What's the antiderivative of 1 over x? Natural log absolute value x, and we're evaluating that from 1 to t. So if we then do that, we have the absolute value of t. Oops, sorry. We'll do this. Natural log absolute value t minus natural log absolute value 1. Everybody's okay? The absolute value of 1 is 1, and the natural log of 1 is
E?
not e. What is it, Alice? 0. The log, any log of 1 is 0, because any number other than 0 to the 0 is 1. Remember, log is like the inverse operation of exponentials. Okay, so what we're left with then is just to evaluate the limit as t goes to infinity of the natural log of t. What's that going to be? Positive infinity. That's absolutely right. How'd you know that, Alice? Yeah, like if we think about what the graph of the natural log looks like, it looks like this, right? Since the natural log only works on positive values anyway, like if we go to positive infinity, it's still going to be increasing the whole time. It goes to positive infinity, right? Everybody's okay? So we'd say here, this is divergent, since the value of that area is infinite.
There's no bound on the right side, so it's always going to be.
No. If it's unbounded, it could still be finite. Yeah. If we did the same thing with 1 over x squared, that's a number. The exact same integral, if we just make it 1 over x squared, that has a finite value. Whoa! You're blowing my mind, Mr. Kulik. Let's try another. So here's the integral from negative infinity to 0 of x e to the x dx. Any vertical asymptote here? For x e to the x? No, right? So the only thing we have to worry about is that lower bound to infinity, correct?
Right.
Okay. So we'll limit as t goes to negative infinity of the integral from t to 0 of x e to the x dx. What's our plan for integrating x e to the x? What's that? Parts. Yeah, that's exactly right. We need to use integration by parts to do this. If you try to u sub it, it's not going to work. because the only substitution for u is like x or e to the x, and neither one of those are going to give you a suitable replacement to get something you can integrate. So we are going to do parts. What should we pick as our u? X. And the dv then should be e to the x dx. So du then is just going to be dx, and v is just going to be e to the x. Everybody's good? What's the formula for integration by parts? It's u times v minus the integral, of v du. So far, so good. What's the integral of e to the x? Okay. So now we plug in our bounds. Everybody okay here? Yes, Adrian.
Why is the 0 and the t switch?
Oh, did I put them in the wrong spots? I sure did. Thank you. Yeah, they're not supposed to. I just copied them into the wrong spot. Great catch. Okay. Everybody okay now? Sorry about the mistake. Good catch, and though I appreciate you guys following along. 0 times e to the 0 is 0. E to the 0 is
1.
Okay. What's the limit as t approaches negative infinity of t e to the t? It's indeterminate, right? And we'll come back to that. What's the limit as t goes to negative infinity of e to the t? It is 0. How'd you get that, Mark? Perfect. Yeah. All right, so let's write this carefully. So we have -1, and then minus, and then 0. Real quick, before I continue on, with the 0, were we okay with how Mark got the 0 as the limit as t goes to negative infinity of e to the t? So if I just tried this like as a direct substitution, I'd have something that looks like this, right? Now this is like improper, but it's intuitively what we want. So it's like 1 over e to the infinity, which is just like 1 over infinity, right? Which is 0, right? Like 1 over a million is 0.00001. If I make that number bigger and bigger in the bottom, it's just closer and closer and closer to 0. Does everybody feel okay there? Okay. That's just like a little aside. All right. So to do this last piece, we need to write this as a fraction so that we're able to L'Hopital it. So what I would do to make this a fraction would be to rewrite the exponential piece with a negative exponent. Is everybody okay with what I did there? We see it's still the same thing. Okay. Now we can do L'Hopital. What does L'Hopital's rule say? If I have a indeterminate form that is written as either 0 over 0 or infinity over infinity or, as a fraction, then the limit of that indeterminate form is going to be the same as the limit of its derivative. Or the limit of the derivative of the top over the derivative of the bottom. So what's the derivative of e to the t, of just t? 1. What's the derivative of e to the t? E to the negative t.
1 over e to the t.
Negative e to the negative t. Right? That's a chain rule. Okay. And what do I get when I take the limit as t goes to negative infinity of e to the negative t? 0 again, right? Because it's like 1 over e to the positive infinity, which is the exact same thing we had before, right?
Right, because it's going to get bigger on the bottom, so it's going to make it 0.
Correct. So this is convergent, and it converges to -1. Give me one moment. I don't love that area under the curve ended up being a negative value, and I just want to check to make sure I dropped a negative sign, which is probably, nope, that is supposed to be the answer. Oh, good. Perfect. Everybody's okay? All right. Let's do another example. Oh boy. All right. Sorry. All right. So if we take a look at this one, first thing we look for is a vertical asymptote.
Yeah.
Look carefully. No, why not?
Because it's always in positive.
Yeah, the denominator is always a positive value, right? Because 1 is positive plus, and then x squared always positive. Can't get a 0 denominator out of that. Now let's look at the bounds. Do we have a problem at the bounds?
Yeah.
Yes. What's the problem?
It will go off to.
So what was the way that we fixed that? We break the integral into 2 chunks. We can break it arbitrarily wherever we'd like. Oops, dx. Typically, you want to break it somewhere where it's with a number that's easy to evaluate. 0 is usually a good one if that's an option, because that's when you're doing a definite integral, usually makes life a little bit easier. But there's no reason you couldn't have picked 1 or a half or 42 or whatever your favorite number is. But don't make life harder for yourself than you need to. Brooks.
I think I'm probably just jumping ahead, but isn't it going to be the exact same number on both sides?
Not necessarily. So we'll have the limit as t goes to negative infinity of the integral from t to 0 of 1 over 1 plus x squared dx. And then we'll have the limit as t goes to positive infinity from 0 to t of 1 over 1 plus x squared dx. Is everybody okay? That I'm just going to write them as two separate and then add them up together at the end, just to keep it all in the same line. It just feels easier. Yeah. Okay. All right. What's the antiderivative of 1 over 1 plus x squared? Tan inverse. Okay. But I did it again, didn't I? Alex, I did it again. Ugh. Come on, Mr. Kulik, pay attention to what you're doing. Okay.
Oh, because T is the lower number.
All right. What's tan inverse of 0?
Oh, it's 0.
That's right.
Oh.
Okay. All right. Who knows what the limit as t goes to negative infinity of tan inverse is going to be? Let's look at the graph. Who knows what the graph of tan inverse looks like?
No, it's just one square.
How about just the graph of tangent then?
It's like it's kind of repeating. It kind of looks like an interval if you do it lots of slopes. Yeah. Well, only one slope.
Okay.
Yeah, it's just that.
Everybody's okay? This is the graph of tangent.
Yeah.
What are those asymptotes at? Nope. Negative pi over 2. And then positive pi over 2. Okay. So what is the inverse function going to do? It's going to take the y coordinate and return the x, right? Look at the graph of tangent. Where is the y coordinate negative infinity? At negative pi over 2. Where is the y coordinate positive infinity? Positive pi over 2.
Wait, is tan inverse the same?
Well, it's taking the y coordinate, returning the x.
Oh.
Right? So if I were putting in the y coordinate negative infinity, it should return the x coordinate from the tangent graph. Does that make sense?
Yeah.
So most of you probably could not have drawn the graph of tan inverse from memory. I'm hoping many of you would have been able to draw the graph of tan from memory and just know what we know about inverses to be like, okay, that's going to be good enough for me. Is that okay with everybody? So what am I going to get here when I add them together? Pi. We're okay with what we did there? How's this going so far? It's all right? Okay. I like this topic because it forces us to review a lot of limit stuff that's been a while since we've thought about. It's coming towards the end of the year, and that stuff like circling back is going to be on your AP exam. So it's nice to think about it again here in this last month or so. It is like a full circle. So this piece that we identify as property 2 is not something you need to memorize. But if you go through your entire Calc 2 class, the second half of Calc 2 is going to be talking about like convergence and divergence of series. And one of the things you'll use is a p-test to do that. This is basically the p-test that says if you have a fraction 1 over x to the p, that series is going to converge. Because remember, an integral is really just a infinite series, right? You're adding up infinitely many rectangles. That's what an integral is. So it's really a series. It's just a infinite series. So that's that. That's why I knew that 1 over x squared, if I did the same integral, would converge, but 1 over x will not. Okay. Anyway, I just wanted to mention that. We're not going to use it. Let's look at the next one. First thing we look for is vertical asymptotes. This is 1/2 one. At what value? 2. Okay. Where is 2 at? The lower bound. So when we do this, it's going to be the limit approaching 2 from the right. Because we're looking from 2 to 5. So we're looking at the right side of 2. Everybody so far so good? How are we going to do this one? I love that. The u will be x minus 2. So du is just going to end up being dx.
Whenever x is just by itself like that, even if there is another like constant, whatever it is du always going to turn out to be dx? Right?
The derivative of x is 1, right? And the derivative of constant is 0?
Yeah.
Okay. Oops. Forgot my integral. Everybody's okay with the substitution we made? Let's keep on rocking then.
Why is it 2 from the right-hand side?
The interval's from 2 to 5, right?
Okay. Yeah.
Which side of 2 are we interested in?
The right side.
Yep. And let's just cut out the middleman. Is everybody okay with what I did there to get the antiderivative? All right, and we plug some stuff in. So that's going to be 2 square root 3 minus the limit as t approaches 2 from the right of 2 times that. How do I do that limit? Just a direct substitution, right? What do I get? 0. So I'm just left with the 2 root 3 then. So again, we got a converging integral. So far, so good? Everybody's all right? We're on board? Okay. I got one more to do. If I look at this one, first thing we look for is vertical asymptote. Do I have one? Yes. Where is it at? 1. Does that matter to us? Yes, because 1 is between 0 and 3. Everybody's okay? So I'm just going to split this into the integral from 0 to 1 and then plus 1 to 3. And then the 1 is going to turn into a t, and I'm going to have two separate limits to deal with. Does everybody feel okay with that setup? Okay. So just like before, 0 dum-dum 1, and that's minus. And then my other piece, that's supposed to be a t. Okay. Is everybody okay with the set? Supposed to be a t. What's the antiderivative of 1 over x minus 1? No. Use a u substitution and a natural log, right? Okay. That's supposed to be a bracket. That's supposed to be an absolute value. Okay. All right. What is the limit as t approaches 1 from the left of the natural log of t minus 1? When I get a direct substitution, what am I getting? What's the natural log of 0? Nope.
0.
Nope. Close. It's negative infinity. It's not indefinite. Think about, what does the graph of the natural log look like? Right? Looks like this. When we're going to 0 from the left, right? And this is automatically, I can say, divergent, because I have one part that's infinite, right? Is that okay? I think. Let me double check that. Unless I shouldn't be able to do any fancy dancy stuff there. Yeah, okay, good. Textbook agrees with what I got. All right. The last idea in here is, again, not something that I would ask you to use, but I just want to preface as this is a foundational idea for the second half of Calc 2 when you compare it, looking at the convergence and divergence of series. Sometimes they'll give you a series that you can't evaluate on your own. What you'll have to do is you'll have to say, oh, what if I compare this to something that I know is convergent or divergent, like one of those P integrals we just talked about. If I can show that what I have is always less than or greater than one of those P's, then I know what the P's do, so I know what that thing's going to do. And that's the idea, okay? So again, very much like the, kind of like the squeeze theorem happening here, that if I have something that's less than or equal to a convergent, then it's convergent. If I have something that's, like something that's less than or equal to a divergent, then it's, greater than or equal to a divergent, then it's divergent, right? That's the idea. Does everybody feel cool? So, a couple problems here to practice from 7-8. And that'll wrap up today. Thanks, guys. When we get back, we have 2 sections to do. A little bit more differential, and then another integration technique. That's going to be the end of content for Calc for this school year for me. The rest of our time will be doing some testing and some test prep, and we're out. I'm still kind of working on test 7 format. So when you guys get back, I'll be able to talk more about what my plan is there. And then we'll just be reviewing after that, okay? Brooks, what's up?
Can I ask you a question with the last? Can I just walk up and blank?
Sure.
How did you, where did you get this equation from?
I did the definite integral. So I have plugged in t and then subtracting it from 0 plugged in.
Oh, why is it? I thought this was and then you just do that side. Okay.
Okay.
Cool. Yeah,
Okay, sure.